Good afternoon, or good morning, everyone. Sorry we're getting started a little bit late. Our microphones disappeared, but we're ready now. So I'm Aparna Sinha, Product Manager for Kubernetes and Google Container Engine at Google. And we have Robert Bailey. He'll be joining me for this talk. He's a staff engineer on Google Container Engine as well. So I think everyone here knows that Kubernetes is a platform that runs across different types of clouds and has broad industry adoption. Obviously, this was something that was a project that initiated at Google and is open source and has a booming community around it. But also, there's a hosted version of Kubernetes at Google on Google's cloud, and that is what we call Google Container Engine. And it kind of serves as a reference implementation. It also provides feedback back to the community about features. And so we're going to talk about Google Container Engine today, some of the customer architectures and some of the feedback and features that customers use, Kubernetes features that they use on Container Engine. So first of all, Google hosts and operates the open source Kubernetes code on virtual machines in Google's compute engine platform, which is our VM offering. It is pretty much pure open source, and it is something that releases within a few days of the open source Kubernetes release. Also, as of the last release, we are offering alpha clusters where you can test out alpha features. So really enables the fastest way to try out and also the easiest way to try out Kubernetes features and provide feedback. So the first version of Kubernetes was released in July of last year, and GKE actually followed after 17 business days. And that was some of the feedback we got at that time was, wow, it takes a little bit of time to get this. And then if you look at the sequence of releases, this is work that we've been doing with the community to accelerate the release train. After the first release, it was a couple of months and then a little bit longer until the next one. But we've been working very actively to make that a constant release train that's about 3 months process at a very regular interval. Simultaneously, inside Google Cloud, we've been working to make sure that GKE actually releases in very much lockstep with the Kubernetes releases. And so you can sort of see that gray box of time delay has shrunk. And in fact, in the last release, it was just 1 day. And so one of the purposes of Container Engine is to make sure that the speed between innovation and users being able to access that innovation is as fast as possible. I will mention that there's a process to roll out Kubernetes on Google's cloud, and that is an automated rollout tool that does that process. But since it rolls out into multiple regions, it takes a little bit of time just per the cloud policies. Also, when we roll out a new version, that means that the new version is available for new clusters and new masters. But the existing masters are not upgraded immediately. There's a time gap until everything is stable, and then those masters are upgraded automatically. So again, the goal here is to shrink the time from innovation to user feedback. So one question is, what is the value of this container engine to the community? And really, from the very start, the value has been, one of the core values has been improving the product quality. So even in the beginning, the community would look to Google Container Engine to be a signal of a release being ready for production and ready for deployment. Also, we get a lot of customer issues early on. We see them since this is the earliest availability, and we fix them and upstream them directly. So in 1.3, there were issues with DNS and with storage, and you'll see that all of those fixes are back on GitHub immediately. Secondly, Container Engine provides a testing and training environment. So a lot of on-premise customers, on-premise users, and and also users in other clouds will try out Google Container Engine just to get started with Kubernetes. And it's a very easy way to get started with the features of Kubernetes. And lastly, we've been getting good feature feedback on especially some of the alpha features. So stateful set, formerly called pet set, scheduled jobs and init containers. We've gotten a lot of users actually trying those out and giving us feedback about how to improve those. But that's the value to the community. What is the value to the user? So there's kind of two aspects of this. When you want to set up Kubernetes, there are a number of different choices that you have to make. You have to choose your cloud provider, you have to choose your OS image, and a number of other things. With Container Engine, a lot of that is done for you, and so it makes it simpler in terms of choice. Secondly, the installation, this is done automatically. It's just a click of a button, and you install. So that's the other value. And thirdly, perhaps most importantly, is the ongoing management. So the ongoing management and upgrade and repair. And that's really, I would say, the value of a managed and hosted offering. So it makes it so that developers can focus on the app and developing their app. And Google can focus on making sure that the system is running. The second piece of the user value is really kind of independent of Kubernetes. It comes from the Google Cloud Platform itself. And what we try to do is combine the differentiators of the underlying cloud platform with Kubernetes. So some of the features that we'll be discussing and demoing today will be examples of this. But so some of the sort of differentiators with the cloud platform are faster startup times for the VMs, as well as heterogeneous different types of VMs, preemptible VMs, and custom VMs. Also, the Google Cloud load balancing has some unique properties. It's global at an L7 level. We'll be demonstrating some of that as well. And then some of the other features with regard to BigQuery and data store, the customer architectures on Google Cloud make extensive use of these, as well as IAM. Another point here is that the container engine binaries can actually be upgraded on a weekly basis, and in fact they are. So a lot of these cloud-specific features are pushed out constantly, even aside from the 3-month train of Kubernetes. And this is some of the feedback. These are some of the customers. This is not a complete list, but you can see that there's a variety of different companies that use Container Engine. And the feedback that we get consistently is that, hey, it's really nice, it's easy to use. Also, with you managing this, with Google managing this, I'm able to focus on my application. And in fact, it's nice that it runs so with high performance and so seamlessly. So this is what it looks like. I think hopefully most of you have tried this out, but it's really a very simple UI, and you can go and create a cluster with the click of a button, the Create Cluster button. And there's also a built-in command line interface. So the Google Cloud Console has a built-in command line interface which launches this CLI, which has both kubectl and gcloud already installed. So this is where the whole installation process is just greatly simplified and allows you to get started in a matter of minutes without having to worry about all of the things that are underneath it. But in this talk, we're going to talk about some of the things that are underneath it. What do you get when you set up a container engine cluster? So the whole process takes about 3 minutes to set up a cluster. You click that button, and in 3 minutes you get however many nodes you wanted with whatever features turned on. You can turn those on in the UI. But what is happening behind the scenes, there's quite a bit happening, and that's why I have the picture of the iceberg. First of all, we are checking to make sure that the user is authenticated. We are also checking the IAM policy to make sure that you have the credentials to actually run the command that you want to run, if it's to create a cluster or if it's to add a load balancer, you have that privilege. And all of that is done behind the scenes by calling the Google Compute Engine API and starting the master and the node. So that is really the technology behind that is the Container Engine API, which is a CRUD API for container clusters. It also is what we use to upgrade the Kubernetes version for the cluster, and obviously is integrated with all the different GCP features. And we own and manage the master. And we're going to talk about how we monitor the health of the master and repair it, and also maintain a set of add-ons. These are actually default add-ons. Most of them are what you would use in a reference implementation from the open source as well. So, and this is a picture of the master and some of the things that are on the master. So it looks very similar for those of you who are familiar with running a Kubernetes cluster either on-premise or on GCE or on AWS. I don't think there's anything here that will surprise you. So it's just that this control plane is managed by Google, and it looks like a black box API endpoint to the user. So in addition to, we're using etcd and API server and the scheduler and the controller manager, these are all standard components purely as they are in the open source. In addition to those, there's an L7 Ingress controller and cluster autoscaler, again, also pure open source versions of this. But these are the things that interact with the Google Cloud Platform. So the Ingress controller interacts with GCLB, Google's Cloud Load Balancer, to set up the global load balancing. And also that master is backed up regularly on an automated schedule. So we ensure that it's always available. And then some of the things that are done behind the scenes, obviously kubelet and Docker. So kubelet is the agent on the node, and Docker, this is all automatically installed, kube proxy, and then a number of default add-ons. So this is the stuff that is, you would do it yourself if you were doing it in an on-premise environment, but this is done automatically. So specifically, the add-ons that we have FluentD and kubedns. FluentD is for log collection, and it runs on every node. It collects the logs and exports them to Google Cloud Logging, and through Stackdriver. And then kubedns enables the service discovery within the cluster. And then the additional 3 add-ons, Heapster is what we use for aggregating all the monitoring and event data. This is, again, same as what is available in the open source. And we're going to talk a little bit more about monitoring in just a second. And then the L7 load balancing backend and the dashboard. The dashboard UI, I think there was a demo of it and a talk on it earlier yesterday. Okay, so that's kind of the architecture, not very different than what you would encounter anywhere else. But what are the things that we do sort of to take user feedback and automate the system even more? This is actually, one second. This is a chart of some additional features that we've kind of automated or built based on user feedback, and it shows the percentage of clusters that are actually using this. So Google Cloud Monitoring, Ingress Load 7 balancing, cluster autoscaling, node pools, and alpha clusters. And these have been ordered actually based on how well they were adopted, but also how recently they were introduced. So you can see that alpha clusters was introduced very recently, and so it's still not available on all clusters, and so it's not as well adopted. Whereas monitoring, which is turned on by default, is pretty much adopted by everybody. So we'll go through each one of these and talk about how users are using it and what feedback they've had. So first of all, for monitoring, monitoring has 2 purposes. One is internally, Container Engine collects metrics from the master to make sure that the master is healthy, and also to repair it in case it is not healthy, and to scale it with the needs of the rest of the cluster. It's also what we use for billing based on how many nodes are being used. And so these metrics are collected directly from the master and then used internally by the service. Secondly, in terms of user monitoring, so the way that user metrics are collected is through the Heapster add-on that I mentioned earlier. There's a C advisor that runs on every single node inside the kubelet agent, and it gathers statistics from all the containers in your cluster and exports them via REST API. Heapster runs in just one pod per cluster, so it's cluster scoped, and it collects and aggregates all of these metrics. There's no special access. And then we pull these metrics and put them into a storage backend, and then make them available through Stackdriver. They're made actually available through Stackdriver as well as through the dashboard UI. So you as the user can view them, consume them, use them in any way you like. And they're also used by some of the other controllers in the system. So for example, for the horizontal pod autoscaler, it uses these same metrics as well to scale up your service. So as I mentioned, Stackdriver and Dashboard UI provide these metrics to you, but also it's a fairly open system, and users can plug in their own add-ons for specific things that they want to do in terms of monitoring. And this is an example of where the open source ecosystem is really available in Google's cloud. And many of our customers actually do this and use these add-ons. And I'll talk about, so Sysdig, Prometheus, Datadog, these are some of the common ones. They have different deployment methodologies. Datadog is deployed as a daemon set. Sysdig is actually a kernel header. But I'll talk about what users do with these. And this is some of the feedback that we've received. They really like having additional options and the flexibility of choosing the monitoring solution. I've heard all of these actually being used in different situations. A lot of the common requests are, they would like to see a particular UI presentation or would like to cut the data in a certain way. Datadog does a really good job of providing a great UI. Oftentimes they're looking to be able to see the resources in the cluster in a certain hierarchy based on labels and have the different views. Also, customers often have different parts of the organization that are used to using a different tool or would like to use a different tool. And so being able to plug that in as a daemon set or whatever in a different container allows different organizations to plug in their specific monitoring solution. The other use case is really for hybrid cloud. So if you're running a cluster in Container Engine and another cluster on-premise or another cluster in AWS, you would want to aggregate your metrics across those clusters. And so being able to install something like Datadog or Sysdig allows you to have a more global view. So that's monitoring. The second sort of additional feature that's actually very popular is Ingress L7LB. And actually, I would say it's also very powerful. So many of our customers who are global and global gaming companies or companies that have IoT solutions that are available in multiple geographies like using the Ingress L7 load balancer. So the Ingress resource itself is no different than it is in the open source. Essentially, customers want to be able to send traffic based on the URL to the appropriate part of the cluster. And that's what Ingress enables. It does the mapping between the L4 service and the URL based on where it should go, based on a map that the user provides. And it is supported by Nginx and HA proxy and also has SSL support. So this is identical to what is available in the open source. What is kind of different in Google's cloud is really the cloud load balancing capabilities, which we're very proud of these capabilities. But essentially, the Google Cloud Load Balancer has the forwarding rule, the URL map, and then the backend service. And we have a controller, the L7 Ingress controller, pre-installed as part of the master to set up this Google Cloud load balancing. Some of the additional features that are unique is, you can get round robin or you can get session affinity. And I think maybe the most unique piece is that it can handle, scaling from 0 to millions of QPS. And that's something that obviously has been very important for some of the larger global customers. Also, GCLB offers cross-region load balancing, and this is kind of unique amongst cloud providers. It's actually not as usable by the simple Ingress object, but where it is really usable is with the new 1.4 release of federated Ingress. And federated Ingress makes it possible so that you can use a single API endpoint, a single service endpoint to distribute your load across multiple clusters, multiple regions, and multiple clusters. And that's currently only possible on Google Cloud because of GCLB's capabilities. So that's federated Ingress. There's the next set of features is related to autoscaling and node pools, and Robert will come up and talk about those as well as give a demo.
Great, thanks Aparna. So as Aparna mentioned, we're going to talk about cluster autoscaling next. So one of the interesting things is, next slide. I have to do this. There we go. As we were building GKE, we got a lot of feedback from customers that they wanted to have their cluster be more elastic, right? One of the advantages of running your cluster in the cloud is that you're not running on sort of a fixed set of resources. And as we looked at how to implement cluster autoscaling, we decided that it would be very important to build this functionality into the open source Kubernetes instead of building something proprietary just for ourselves. And so what we did is we started building a very flexible controller. It's in the contrib repository. And we built hooks just to plug it into the Google Cloud provider, right? Because that was our immediate need to meet our customers' goals. It's currently in beta. It's very conservative in terms of how quickly it scales up and down your cluster, but it's already proving really valuable to our customers. And it's actually proving so valuable that people have ported it to also work on Amazon. And so one of the advantages of us having built it in the open source community is that now it's being taken advantage of across the wider community, and it's not just specific to Google Container Engine. It'll scale up based on pending pods, which is really nice because if you just look at CPU utilization across your cluster, you can very easily get into a state where you have very low CPU utilization because pods are scheduled based on resource reservations and not current resource usage. And it's impossible to schedule new pods into your cluster. But when you want to schedule a new pod, there's nowhere to place it. But an autoscaler that's just looking at resource utilization will not actually scale up your cluster. So if you look at resource requests, then you can tell that a new pod would be able to schedule if you add more nodes to your cluster. You can dynamically add a node, and then you can see that that pod gets placed on the new node that you added. So some of the things that customers say is that they really like the feature. They've obviously requested it. They're concerned about how conservative the feature is right now. We started off very conservative because we didn't want to have a cluster that was very rapidly growing and shrinking. And then the other problem is that the cluster autoscaler, it tries to do a good job of picking which nodes to remove when it schedules down. But it's possible to get into a state where you remove a critical node and actually disrupt service. So some things we're looking at integrating the cluster autoscaler with before it reaches general availability is things like pod disruption budgets, where when you schedule your pods, can tell people or tell the system exactly how often the pod is allowed to be rescheduled. And the cluster autoscaler can take that into account when it's removing nodes from your cluster, and it can choose a node that will keep you within the SLO for your pods. And then also integrating it with forgiveness and graceful termination, so that when you're deleting containers, you actually send a signal to the container and let it know that it's about to be removed, so it can do like local cleanup and flush data to disk. So the next thing we're going to talk about is node pools. So node pools are sort of another interesting set of feedback that we got from customers, where internally at Google, pretty much everyone who wants to write a service doesn't care what type of machine they're running on. Like, you write your code, you give it to Borg, and it just runs, and you don't worry about the underlying infrastructure. And this is sort of what we started building with Kubernetes and with Google Container Engine. And so you could launch a cluster, you tell it what you want your underlying infrastructure to look like. I want 2 cores per machine or 4 cores per machine. And users sort of very quickly turned around and said that they wanted more flexibility. They wanted to be able to change the type of machine they were using. They guessed wrong when they created their cluster, and now they decide they need 8 cores instead of 4. Or they decide that, I want to have labels on different types of machines. I want to isolate my workloads. I want to be able to put labels so that some of my users can run stuff on some nodes and other users can run stuff on other nodes. Or they might have a use case where they need some nodes that have a lot of memory but not much CPU, and some nodes that have a lot of CPU but not as much memory. So we sort of consolidated all of this feedback and built a feature that we call node pools, which is sort of really just simple layering on top of the basic Kubernetes concepts, where you can have multiple groups of homogeneous nodes instead of a single group of homogeneous nodes. And this sort of allows you to get all of those sort of requested features that I just mentioned. You can have multiple node pools, which can give you different types of machines. You can create new node pools, which can allow you to transition the type of machine that you're using. You can add custom labels to those machines. And you can also use node pools for things like upgrades, which allows a better upgrade story. So this is a great example of us sort of listening to users and sort of taking that feedback into our product. And we did it in such a way that it actually sort of works across other providers also, because really node pools as a concept is us applying special labels to nodes in specific groupings. And you can do the same thing if you're running on-prem or on AWS. If you're running on-prem, you might want to label all of your nodes with which failure domain they're in, like which rack or which data center. Nodes already report their resource type. You might want to give them custom labels, like this should be a dedicated machine type. So all of the sort of things that we're building around node pools are sort of very portable to other operating environments. Here's sort of a couple examples of how node pools work. You've got one node pool with one version of Kubernetes, and then another node pool with different size VMs. I went through all of that already. And then lastly, we have a couple of examples of user feedback from people that are actually using node pools in their production systems. So we had 2 different customers who both started off at that top state where they had a node pool with a 1.3 version of Kubernetes. And we had one of the users decide they wanted to use a different base image, right? So they wanted to transition from the container VM base image to our Google Container VM base image, and they created a new node pool with that type. And we had another user that wanted to upgrade, and so they created a second node pool and upgraded their system to the second node pool. All right, so now we're going to switch, and I'm going to show a quick demo. The demo, again, I mentioned earlier, autoscaling is a bit slow. So for the demo, I made a recording last night, and I'm just going to play that instead of trying to go through autoscaling, because otherwise it would take about 20 minutes.
I just wanted to add that the demo that Robbie's going to do is an actual thing that a customer has used Autoscaler and node pools for. So this is reenacting basically what a user has done. All
right, so I'm going to give a sort of a voiceover here as I walk through the demo. So the setup is we're going to do a very small scale demo. So it's not actually the scale demo, but this is a really good sort of sample application you can run. The code for all of this is open source. It's in the Contrim repository. Basically, you run some Nginx servers, and then you run some load testers, and you're sending load to your Nginx servers. So what I've done to set up is I've created a cluster with a single node pool. Now I'm actually launching the scale demo. So we launch a couple of different services and controllers. And then we're going to scale both those up. And you're going to see we're going to send about 10,000 requests per second to a number of backends. And you can see all the pods that are launching in the cluster. Each of the load testers sends 1,000 requests per second, so we need 10 of those to get up to 10,000. It takes just a second for them all to start. And then what we're going to do, you can see here that the node version is 1.3.10, which is not the current node version. There's an update available. So one option is to click that button and to say, update my nodes to the latest version. Some people want a little bit more control than that. And so one way you can have more control is you can create a second node pool at a different version. So what I'm going to do is I'm going to create a new node pool. You may not have caught this, but the first node pool had 4 core machines. The new node pool I'm going to make have 2 core machines. So this node pool is going to have slightly smaller machine types. I'm actually integrating in one of those use cases of changing the machine type because I guessed wrong when I created my cluster. I've also enabled the autoscaler for my new cluster. So what I'm doing is I'm making the new node pool really small, and then as I move my workload over, it's going to auto-size itself up to be appropriate for the amount of work I'm running. I could have also added an autoscaler to my existing node pool, which would have most likely shrunk it down because it was quite over-provisioned. All right, so we see 2 new nodes are now in the cluster. And now the first thing we do as we're going to upgrade from the old node pool to the new node pool is we're going to cordon all of the old nodes. And what this does is it marks all the old nodes as unschedulable. And what that will do is it means that when you try to reschedule your work, when you drain the nodes in the next step, it will force the pods to be moved over to the new node pool. If you skip this step, then when you drain a node, the pods can be rescheduled onto other nodes in the old node pool, which means when you drain that node, they'll get rescheduled again. So this is really sort of an optimization to make sure your workload isn't rescheduled more often than necessary. Next, we're going to migrate the workload over by draining. And after each drain step, you might have missed that. After each drain step, we're actually going to delete the old node. So at the end of the demo, the old node pool will be all the way down to 0 nodes, and the new node pool will scale up to however many nodes we need to run our entire application. If you look over here, we're running get pods, and you can see the node on which each pod is running. And all of the pods, well, not anymore all of them, a couple of them have switched over to the new node pool, and many of them are still running on the old node pool. And then down here, you can see one by one, all of the nodes in the old node pool become not ready and then disappear as we delete them. And you'll start to see new nodes get added at the bottom. So we started with 2, we're already up to 3. And as we move through this sped up part of the demo, you'll see new nodes show up as not ready and then flip to ready. And right after they flip to ready, you'll see up here that one of the Nginx instances that was previously unschedulable because there was no space in the cluster switches to be container creating and then in the running state. All right, so now we're up to 6 nodes, and we have one more Nginx instance that's not running. And here comes one more node. Great, so we're now back up to 6 Nginx instances. We still have our 10 load bots running. We were serving all 10,000 requests the entire time. And you can see if you drill into the cluster that the old node pool is now shrunk all the way down to 0 because my shell script was deleting one node at a time, and the new node pool has scaled itself up automatically to 7 nodes. So that's sort of an example of how you can combine this concept of node pools with cluster autoscaling to do sort of a seamless upgrade. Obviously for the demo, I did the upgrade much faster than you want to do in production. You know, there was a very short sleep between each drain. You'd want to do that much more slowly. You can do it at whatever sort of level of granularity you want, right? You can do it manually, you can automate the process, but it gives you a lot of control over exactly how you upgrade your cluster. All right, so. All right, and lastly, we're going to talk about alpha clusters. So Aparna mentioned earlier that alpha clusters are something that we recently added to Kubernetes. Again, this was based on user feedback where users would see something being developed in open source. Oftentimes when you're launching a service as a large company, no one knows what you're working on, right? And so you just kind of work on it and then you put it out there and people can use it. But with Kubernetes, everybody keeps asking like, oh, I see scheduled jobs or I see pet set, like why can't I use that in GKE? And the answer is that alpha features are very unstable, right? You can see with pet set that we just renamed it to stateful set. And there's no real upgrade path between those 2 versions. But that doesn't mean that people don't want to try it. And so what we've done is we've created a way for people to launch clusters that have all the alpha features enabled so they can try out the alpha features before they're ready for production. And this turned out to be a really great way to get feedback for those features before they become sort of locked into their final API state. And so for pet sets and init containers and scheduled jobs, we're getting a lot of feedback from the community because people can go into GKE, click a button, have a cluster, try out these new features with the caveat that that cluster is not really ready for production and won't last for very long. And that's the end. So I think we have a few minutes left for questions before we get kicked off the stage. Yeah, so that's a really good question. The question was, the node pools underneath use something we call managed instance groups in GCE. And you can actually turn on a GCE autoscaler on the managed instance group. And we actually tried this. So this is what I was referring to when, if you just turn that on and you tell it to look at the CPU utilization, you get really terrible behavior. Because the autoscaler is assuming that all of your nodes are effectively the same, that any of them, if you add a new one, it's going to have the same behavior as the existing one. So if it sees the overall utilization go up, adding another node should make the overall utilization go back down. It turns out with Kubernetes, since people schedule pods and pods don't land exactly evenly across all nodes, and some pods have higher resource reservations, that it kind of breaks down really quickly. And so we realized that we couldn't just flip on the autoscaler, and that's why we ended up building sort of the custom cluster autoscaler for Kubernetes. Other questions? Oh, yeah. Right, so the question is the Heapster pod is running as a single pod. It's actually running underneath a replication controller. So it's a replication controller with one instance. So there is a single pod running, but there is a controller making sure there is always a single pod running. So if it gets killed or if that node gets removed, then a new instance of Heapster will get started.
And we monitor it.
Right, and we also monitor that it's running. Although if you scale yourself down to 0 nodes, then it's impossible for it to run. So, one more question. Right, so the system has a notion of forgiveness, which is we anticipate that there are going to be times when a node gets sort of disconnected from the rest of the cluster, and we might not be hearing from it. And so there's a period of time in which a pod can be not running, but we don't know about it for a while before it gets rescheduled. So if the node actually disappears, we can usually detect that pretty quickly because we can talk to the Google Cloud Platform Compute Engine API and find out that the node is gone, and we can kill it immediately. But if we just stop getting status about that pod, then yeah, it can take 5 minutes before a new one starts. That's the default threshold.
What do you use for config management of machines?
The question is, what do we use for config management of the machines? Which machines are you talking about?
The machine that make up our GKE cluster.
Yeah.
I check my features and say I need this add-on.
Right, so to actually configure like the underlying machines, we use all the scripts that are in open source. So if you look in the cluster directory in open source, there's a bunch of cluster GCE machine configuration scripts that are used to configure all of the nodes that run in the cluster. You can then on top of that run like a daemon set that tries to reconfigure all of the nodes in your cluster if you need to make customizations. Say that again? Right, so the question is, does upgrade follow the same path? So what happens with upgrades is when an upgrade comes out, we upgrade the master machine for you, and then it's up to you to upgrade your nodes. And the reason for this is that we found that node upgrades can be disruptive, right? And we want that to be under your control of when that happens and the speed at which it happens. So as I mentioned before, when you want to upgrade your node pool, you can click a button and we'll upgrade your node pool for you. Depending on your application, that can be perfectly fine, but it also might break your specific application. So you can also create a second node pool and you can migrate your workload over, which is what I showed during the demo. If you have a daemon set that you've deployed and there's an upgrade, then it's up to you to upgrade that daemon set to a new version that will work on the new nodes. Generally, most of the time, they are still okay, but there are definitely cases where there's a new kernel that comes out that's incompatible with a tweak that you've been making to your nodes. And again, that's why it's sort of on you in terms of scheduling when you're going to upgrade your nodes, because then you are breaking yourself instead of us breaking you, maybe at 2 a.m. in your time zone.
And the two features that Robbie mentioned with regard to pod disruption budget and graceful termination, those are work in progress for the upcoming release. So you can read about them on GitHub. But they will allow, at least for nodes with the default node image, which is Google Container Image, GCI, for you to opt into node upgrades managed through Google. That's not yet available, but it's coming with those features.
Yep. It's just a 2. We're still trying to figure out how to make it possible to have people bring customized images. It's a very difficult problem because everyone has sort of their own pet image. It's not sort of clear exactly how that will work with the rest of the system. And we want to make sure that the experience people have is a functioning Kubernetes system. So as an aside, during the alpha version of Google Container Engine, you could actually specify a specific node image for your cluster. And we found people were specifying like, oh, here's my Windows image, please launch that for me. And we'd be like, oh, this cluster didn't create, I wonder why. Like, oh, they're trying to launch Windows, or they're trying to launch, Ubuntu or Red Hat or some other system where the machine configuration part didn't actually work, right? And so it was impossible for us to give them a functioning cluster, which is a pretty terrible user experience. So we want to make sure the user experience is really good before we allow that to be more customized.
And that's specifically for the node-based image. So there's only the 2 options, which is the Debian-based container image and GCI, the Google Container Image. If you have specific requirements, then you can use GCE. You can always set up a Kubernetes cluster in Compute Engine, and then it doesn't have all the automation, but then it has 100% flexibility.
I think if there are any other questions, we'll wait up front because the next talk is supposed to start in about 3 minutes. So, all right. Thanks, everyone.